Hello, sir.
Yes, ma'am.
Okay, sir, I will start from here.
Okay.
Yeah, okay. So, good morning, Dr. Suresh, and good morning to the participants who are watching this live session. So, welcome to today's session on the structural response of carbon nanotube, the toughened glass fiber reinforced composite panels is subjected to underwater shock loading. This topic is at the forefront of materials science and engineering, is combining the remarkable properties of carbon nanotubes with the strength and the durability of glass fiber composites. These advanced materials are crucial for applications that require exceptional performance under extreme conditions, such as in marine and defense sectors, and understanding the behavior underwater shock loading is essential for improving the safety and reliability of structures exposed to such an environments. In this session, we will explore the intricate the mechanisms that govern the performance of CNT, toughened glass fiber reinforced composites when subjected to underwater shock impacts. The incorporation of CNTs into the composite matrix significantly enhances the mechanical properties, including tensile strength, toughness, and energy absorption capacity. This enhancement is vital for mitigating the damage from underwater explosions and impacts, which can have devastating effects on marine structures and vessels. We will examine experimental studies and theoretical models and simulations that provide insights into the dynamic response and failure modes of these composites under shock loading. Our discussion we will also cover the practical implications and potential applications of these advanced composite materials. By understanding their structure response, we can design more resilient and durable marine infrastructure and submarines and underwater vehicles. Additionally, we will highlight the ongoing research and future directions in this field, emphasizing the need for continued innovation to fully harness the potential of CNT toughened glass fiber reinforced composites. We hope this session will provide the valuable knowledge and stimulate the further research and development in the field of underwater shock resistant materials. So before we start Dr. Suresh session, I would like to give some short introduction about him. So it is with great pleasure that we introduce Dr. C. Suresh as esteemed associate professor in the Department of Aeronautical Engineering at the Global Academy of Technology in Bangalore. Dr. Suresh brings a wealth of knowledge and experience to his field and earned through the years of dedicated academic pursuit and professional engagement, and holding a PhD in aeronautical engineering from the Hindustan Institute of Technology and Science. And Dr. Suresh's research is deeply rooted in the complexities of fluid structure interactions and particularly focusing on the large deformation behavior of thin rectangular plates subjected to underwater explosions. His academic journey, which includes an MTech and BE in aeronautical engineering, it reflects a strong commitment to advancing the understanding of aerodynamics and structural integrity under extreme conditions. So, Dr. Suresh's professional trajectory underscores his dedication to education and research, with significant contributions made at various esteemed institutions and research organizations. And prior to his current role, he served as an assistant professor at the Institute of Aeronautical Engineering in Hyderabad and at the Hindustan Institute of Technology and Science in Chennai. His tenure at the National Aerospace Laboratories in Bangalore, where he worked as a graduate trainee in the Experimental Aerodynamics Division, further solidified his technical expertise and hands-on experience with advanced simulations tools such as LS Dyna and ANSYS. So, Dr. Suresh has also played a pivotal role in guiding projects and funded by the Defense Research and Development Organizations, the DRDO, focusing particularly on the effects of underwater explosions on composite structures and shock impact on underwater bodies. Beyond his academic and research endeavors, Dr. Suresh has actively contributed to the broader engineering community through organizational and training initiatives. He has successfully organized international conferences and workshops on drone building, reflecting his commitment to nurturing the next generation of aeronautical engineers. As a reviewer of PhD, these and journal articles, Dr. Suresh has upheld the rigorous academic standards and promoted excellence in research. His contributions have been recognized through awards for research promotion and teaching excellence, further solidifying his position as a leading voice in the field of aeronautical engineering with numerous publications and conference papers. To his credit, Dr. Suresh continues to push the boundaries of research in fluid structure, interaction and impact analysis and fatigue analysis and leaving an indelible mark on the field. So at the end, I would like to introduce to the motto of Dr. Suresh. The main motto is a striving for excellence through innovation and education. So I would like to hand over the session to Dr. Suresh and also thanks a lot for joining us today and over to you, sir.
Thank you, ma'am. Thank you for the introduction and giving me opportunities to present for Teams Tech Solutions. And I would like to extend my welcome to Suganti for inviting me for this section. And I welcome all the participants for this session. And I feel free to ask any questions at the end of the session. I'm ready to answer all your queries to my extent. So we'll start with the session. Is the screen visible to audience, man?
Yeah, yes, sir. You can continue.
Yeah. So I will welcome once again all the participants for this session on structural response of carbon nanotube toughened glass fiber reinforced composite panel subjected to underwater shock loading. So why this session is important and why we need to learn or gain knowledge in this domain is so in recent years all over the world, if you see, there has been a threat related to these underwater explosions to all the merchant ships and submarines. So when the merchant ships are subjected to this type of explosives, lot of losses in terms of wealth it is for every nation is going to take place. So if we to escape or to prevent from such explosives or such threats, we need to have a strong structure which can withstand these low explosive loads which is happening in the underwater. Generally, few things we need to understand how the explosion is happening in air and in water. So generally, all these explosive waves will travel in terms of a pressure wave. In air, these waves will travel with the speed of the sound, which is almost 340 meters per second. In water, it travels at the speed of 1500 meters per second, which means in water it travels 5 times faster than in air. So even if the object is far away in water, the waves will reach very quicker than in air. The second point why we want to learn in this is in air it will decay very fast. The waves will not travel much longer distance. It will decay because air is an when this submarine was going, there was an initial explosion sound which came. But the Russian Navy ship, which was very close to the submarine, realized that something has happened, but they don't know really that it is caused because of underwater explosion. So all the 118 persons on board in the submarine were killed in this explosion. So they Russian Navy came to know that there was an underwater explosion takes place and all the persons are died after 6 hours of this accident has happened. So this is the tragedy in underwater explosion. Like in outside world where the explosion is happened, it will be exposed to the world very quickly and immediately. So the rescue operation will come and they can rescue. But in underwater, when the explosion takes place, it is very difficult to know by the others because nobody is watching the seas and oceans much closely like in our land areas. So whatever happens in underwater is almost critical and more threatening to these merchant ships and the submarines. So another thing is USS Cole. When this ship was going, almost through investigation, they found 200 to 400 kg of high explosive they have used to damage these ships. So this were considered this as an terrorist attack. So almost 17 crew members they lost their life and 39 were injured. So this attack was happened close to the water line. You can see in the image there was a water line. So half of the damage is happened above the water line, and remaining half of the damage happened below the water line. So because of this, not much water is entered into the ship, and before it enters, the rescue team came and they safeguarded remaining. Still, the effect is more because of this damage, and 17% has lost their life in this attack. So these are some of the examples which has happened. This is only few. There are a lot more accidents like this which has happened. So all these incidents and a lot of threats in underwater made me to do research in this area. So mainly, if you see the underwater structures, whatever the vehicle, if you see, it will be the structure will be like a half filled with water and a half filled with air. There will be two structures in between. It will be air and fluid filled. So we modeling these and doing the numerical simulation on this is a challenging task because uh, most of the studies, if you see, only structure will be there, load will be there. Modeling that and analyzing that, it will be much easier. But when fluid is there, when air is there and it is half filled, and modeling that type of structure and understanding its behavior, that is fluid structure interaction behavior, is more complex compared to normal structural analysis. So this field is more interesting, and uh, more only few people are working on these areas all over the world. So it will be this information whatever we are sharing will be more useful for youngsters to come up and work on these areas. So that is the main idea why I am presenting this topic to most you all participants. So there is a continuous need to understand how a structure can withstand this type of loads, and how better we can build the structure for this. So my main area will be focused on how the air-bagged and water-bagged structure will behave, and what type of damages will happen, and which structure will withstand more impact loads. That is what mainly I am going to focus on today's lecture. So for understanding these, doing an real model and doing the testing is very costly, and to make more understanding, the investigation is done using an software called LS Dyna. Mostly this software is used for understanding the impact analysis. It is a nonlinear finite element simulation software. Mostly all the impact analysis all over the world they are doing using this software. So you will understand what type of deformation and failure when the structure is subjected to this shockwave will undergo in deep. So we will investigate about the large deformations and the failures which is happening for glass fiber reinforced polymers. So we have considered a glass fiber reinforced polymer of a 3 mm thickness plate, and we have investigated based upon different amount of explosives when it is subjected to it, how the deformation and everything it is taking place for a structure. So before understanding that, we need to understand how this underwater explosion and how the pressure waves it is can be calculated using analytical ways. So this equation called where PFT is a time dependent pressure. So at whatever the time you want, what is the pressure at this distance can be calculated from this. It will not give the pressure on the structure. For example, I will tell you, if an explosion is taking place in an water at one particular distance, I want to know what will be the strength of this pressure wave after away from the explosion region. That pressure wave and the strength of the shock can be calculated using this formula. So Here, P naught is the peak pressure. So, peak pressure can be calculated using this formula, where W is the weight of the explosive and R is the distance from the center of the explosion to the point where we are measuring. And this T minus TD is the decay time. Okay, so this can be calculated by R minus R naught by C, where C is the sound of the shock wave, speed of the shock wave in the water, which is 1500. R is the shortest distance from that point, and R naught is the radial distance from the structure to the explosive center. So this will, if you substitute all these values in this, you will get what is the T naught. So this equation is given by Cole, and we have one more equation for the same thing which is given by Zamblesky. So he given this equation in two different forms. One, if the explosion is happening very close to the structure. Other one, if the explosion is happening much away from the structure. So for near field and far field, he has just gone in depth and he has classified the same equation for near field and far field. So it becomes more accurate compared to Cole's equation. So if we are dealing with a near field, we can choose that particular equation. If we are dealing with a far field, we can choose that particular deformation. So mainly based upon the distance. So R by R naught ratio, the equation will vary in these things. So the values and the equation will vary. So near field, in Cole's equation, near field, we had got some deviations with the experimental, but it is matching very well with the Zamblowski because of these reasons. So next one is Taylor's plate theory. So far, this Cole's equation and Zamblowski equation will give you what is the free field pressure in the water far away from the explosive region where it is happening. Taylor's plate theory, we will take the free field pressure at that location, and if a plate is there in that location, what will be the pressure which is acting on the plate can be calculated using this Taylor's plate theory, and this will give you the what is the velocity of which the pressure wave is coming and hitting the plate. So this will give you the mass ratio of this. So using this Taylor's plate theory, we can find out what is the pressure which is going to act on the structure from the explosive. So if you see roughly this equation, so free field pressure, let us say it is 150 megapascal. Roughly we can say the pressure on the structure will be twice that because it is two times the free field pressure. So it will be around 300 megapascal on the structure on the same location. So next one, we need to understand what is shock factor, because based upon this only all our studies it is going to depend upon. So it is a factor where we can measure the intensity of the shock. Mainly, for example, in real case, the ship will be much bigger, and the explosion what they are using it to damage that ship also it is going to be much bigger. For example, they are using 200 kg of explosive to damage. In real case, we cannot use actually the 200 kg. But what we can do is we can maintain the same shock factor by reducing it. For example, instead of 200 kg, I am using only 20 grams of explosives to study the same effect. So I have to maintain the same shock factor in real case and in the simulation case. So I can for that this shock factor is very crucial in understanding it. So to simulate the real case, what is the shock intensity and damage, how it is going to take place, this shock factor is very important. So here for studies, we considered glass fiber reinforced composite. Presently, all the submarines, all those things, what they are using is metal structures. But the drawback in metal structure is that they are prone to corrosives. So after certain time, all the metal parts will start corroding. That too, especially in sea waters, because of saltness, the corrosion rate will be much higher compared to our normal water. So these composites are corrosion resistant and they can give for more life for the material. That is the reason why now composites are replacing all the metal parts wherever they are using it. Other thing, whatever the metal strength is there, same strength we can attain using these composites, and with much lesser weight. So strength to weight ratio compared to metals for composites, it is much higher. Even though we have composites, to increase the strength of the composites, there are many types of fillers, like they can add graphene, they can add carbon nanotubes. In carbon nanotubes also, different types of carbon nanotubes are there: single walled carbon nanotubes, multi walled carbon nanotubes, like that. So here we have choose the multi-walled carbon nanotubes to increase the strength of the composites. So we have considered zero point 0.1 weight percentage of multi-walled carbon nanotubes and 0.15 weight percentage of carbon nanotubes. By seeing the color of the composites, you can see when we add the when we increase the amount of carbon nanotubes, the structure color, it is changing close towards black, because carbon's color naturally it is black. So when we keep on adding it, the structure it is so we consider three types of structure. First one is GFRP neat, where no carbon nanofills are used, and the second structure with a GFRP with a zero point 0.1 weight percentage of carbon nanotubes. This weight percentage depends upon what is the amount of resin we are using it. So in total weight we are using zero point 0.1 percentage of the carbon nanotubes, total weight of the resin. So in third case, we are using a 0.158 percentage of multi-walled carbon nanotube. These are the three test samples we are considered for our test. Then to carry out the test, we need to have a fixture. So this fixture is also important. What is the dimension of the fixture? How we can create this fixture? So based upon naval studies and naval structures, we come to we have decided this fixture based upon the structures. So the fixture is totally it will be a 550 cross 450 mm, and the center exposed the area to the explosive will be like uh, 300 into 250 mm. So this is the fixture we have tested all our explosives. So from this we kept the test plate in the fixture, and the red color which is hanging is an explosive. So this explosive and the distance between the structure and the explosive, we have maintained it as 150 mm. So this we call it as explosive bulge test setup, the total setup. So test plate and the explosive will be fixed in this, and the whole setup will be immersed inside the water. So we immersed it to 2 meter depth inside an water tank. So it will be immersed into the 2 meter depth. So the explosive is kept inside a plastic container, and it will be sealed with a tape, so that the water will not enter into the explosives, and a detonator will be there. So after immersing it and setting the whole setup inside the water, we will explode the using the detonator. Once the detonator explodes, then the explosion will take place, and how the structure will damage, it will be measured. So we study about the plain GFRP composites. So we used different types of weights of explosives, like 5 gram, 10 gram, 15 gram, and 20 gram. And as I told, the shock factor. So for 5 gram and 10 gram, 15 gram, and 20 gram, we have calculated the shock factor, and we kept the distance 150 mm as constant for all the tests. And we have measured after the test what is the permanent deformation. So when we use 5 gram, the total deformation of the composite panel at the center is 1.47 mm. For 10 gram it is 11.52 mm. For 15 gram it is 13.73 mm. And for 20 gram, there was a complete damage in the structure, so we could not measure the permanent deformation. Next one, if any tearing has happened, if we see for 5 gram there is no tearing, because the structure withstands that load, and for 10 gram also there is no tearing, but we observed some visual cracks on the surface of the structure. For 15 grams, there was a tearing on the edges. So the length of the tearing we measure it is 214.61 mm, and for 20 grams we have measured the tearing as 239.8 mm. So this double star denotes that the structure is damaged more and it cannot withstand further loading. So the whole ship or submarine will get completely damaged. So in 15 gram, we have seen the composite fiber breakage, and there was a delamination and matrix cracking at the tearing edges. At 20 grams, the fiber is completely pulled out. So same when we continued with a zero point 0.1 weight percentage of carbon nanotubes for 5, 10, 15, and 20 grams. So the damages what it is happening on the structure. So uh, here you can see in previous case for 10 gram the deformation is almost 11.52, but here it has reduced to 5.43 because of adding of CNT. It has given strength to the composites and it reduced the deformation what it is happening on the composites. Same way again here when we go for 20 gram, so there was a complete damage of the structure. We are not able to protect the structure when the amount of weight of the explosive increases. So what are all the observations? I will explain you by showing some images. So this is for 0.15 weight percentage of carbon nanotubes. Same we have repeated for 5, 10, 15, and 20 grams. Distance is 150 mm. So for all the tests we have maintained the shock factor same, and we have observed what is the damage which is happening in for all the three plates. So this is for plain GFRP composites when it is subjected to an explosives. So for 5 gram, we can see there is no visual cracks or damages which has happened. And for 10 grams, we can see some cracks, surface cracks which has taken place in this. And as I told for 15 grams, so there was a delamination in the matrix of the composites and there was a tearing, and one edge of it there was a tearing and we measured the length of the tearing. That is what I was explaining in the previous thing. If you see for 20 grams it was almost teared in all the edges and the complete center structure has been pulled it. So we are not able to measure what is the exact permanent deformation for 20 gram. Next, when we see for zero point 0.1 weight percentage of composites, so there was a slight crack at 5 grams in one of the bolted edges. And for 10 grams, we can see there was a shear out in one of the bolt edges, and there was a slight crack in all the edges of the thing. But the amount of deformation has got reduced when CNT is increased. When we go for 15 grams, the damage was much severe. And composite, what is the drawback is when we keep on increasing the strength of the composites, its brittleness also increases, which means it will not undergo much deformation. It starts failing immediately. So because of that, a lot of damages has happened when the amount of CNT is added because of the brittleness of the composites. So we have seen much more damages in the composite structures when the amount of shock is increasing. This is for 20 gram charge weight. We can see completely damaged structures in all the ends, complete pull out. And again for 0.15 the amount of crack has got reduced compared to zero point 0.1 in for 5 gram. And here also all the edge delaminations and crack got reduced compared to zero point 0.1 weight percentage of the thing. Here also the structure withstands much higher load and the damage is much reduced compared to zero point 0.1 weight percentage of the carbon nanotubes. Here, if you see the damages, whatever happening at 20 gram is slightly reduced, but still we are not able to safeguard the structure from the damages. So next to carry, these are all our experimental test, how the test plate with the different carbon nanotubes behaves. Next, to carry out the numerical simulations, we need to find out the mechanical properties of the carbon composite plates. So we tested uh, in tensile test, and we have estimated the mechanical properties of the carbon nanotubes. So we cut the specimen and we have done the density test by burning the specimens inside a furnace. So before furnace, after furnace, we have found what is the weight, and from the weight we have calculated from the mass and weight we have calculated the density. Then inch modulus, shear modulus, the strength in tensile direction, compression direction, and shear direction, everything we have tested, and we have found out what is the mechanical properties of the composites. So these properties are used to carry out the numerical simulations using LS-DYNA software. Then in LS-DYNA software, this is the complete composite test plate which we have fabricated. In the sidewise, if you see, we have fabricated with a number of layers based upon how much thickness we need. So we can increase the number of layers. So layer-wise modeling is also shown on the and if you see from the front, it will look like a beam, that is composite panel model, and it is meshed using finite element software. And we have fabricated the whole EBT fixture, that is explosive bulge test fixture, and with the bolts and nuts, everything in real case how it is. We have done everything in the numerical, and it is kept inside the water domain. In real case, how we will do same inside the fluid domain, the whole fixture is kept, and the explosive is also modeled using an initial volume fraction option is there in the LS Dyna. Using that, we can convert a part of the fluid domain into an explosive, and we can give the properties of the explosive, so that fluid domain particle will behave as an explosive using that properties. Then we have measured free field pressure, and we have compared with the empirical relationships which is given by Cole and Zamwysky. So for LS Dyna, so we have measured the pressure as a 95.57 megapascal at a certain distance from the explosive, and at the same distance, if we calculate using the Cole's equation, it was 91.48 megapascal, and from Zamwysky it is 92.97 megapascal. So we can see uh, Zamwysky is much closer to the LS Dyna, and Cole is slightly deviating. This is because Zamwysky has classified the equation for far field and near field separately. In Cole, it is a common equation, so Cole was slightly deviating from the LS Dyna results. And then we have measured the displacement, same whatever we have done in the experiments, same we have repeated for numerical simulations, whatever same experimental setup, same way we have done the numerical simulations, and we have measured the displacements of the composite panel, what is the maximum displacement it is going. If you see here, initially this delay is there. It is the time taken for a shockwave to travel from the explosive region to the plate, and then once the shockwave reaches the plate starts deforming, and it slightly oscillates and reaches its maximum deformation. In shockwave, what will happen is the shockwave will go hit the plate and it will travel away. Again, the second set of shockwave will come because of the explosion. So once it travels away due to the elastic property of the material, and this has happened everything in millisecond. You can see it has reached its topmost deformation in almost a point 1 to 1.3 milliseconds. Again, since it is a short duration, due to the elastic properties, the material will come back to its original position. Since it is coming at higher way, it goes to the negative deformation. And again, when the second shock wave comes, it pushes the plate again to the thing. But the second shock wave will be always with a much lesser intensity compared to the primary shock wave. So the deformation caused by the second shock wave will be much lesser. But this second shockwave is more crucial when primary shockwave already crossed the damages. When the second shockwave comes, it will push large amount of water into the hole, and it will make the ship to sunk into the water very quickly. So after that, the next shockwaves and all, it will get decayed, and the intensity will be very less. So mainly we focus will be on primary shockwave, and the second focus will be on the secondary shockwaves. This is for 5 gram charge weight for all the three plates. How it behaves. We need 0.1 percentage and 0.15 percentage weight percentage of the carbon nanotubes. Second, the same experiment is repeated for 10 gram composites. In 5 gram, we could not see much difference between neat zero point 0.1 and 0.15 weight percentage of composites. But for 10 gram, we can see an difference that for point with a neat zero point 0.1 and 0.15 shows much difference in the displacement parameters. So next one for 15 gram charge weight, we can see much differences for zero point 0.1 compared to 0.15 and zero point 0.3. So we have compared all the permanent deformations which take place for experimental and numerical, and what is the deviation in the permanent deformation. For 5 gram charge weight, experimentally the total permanent deformation what we measured is 1.47. From numerical simulation, we got it as a 1.61. So it is almost close, but since the number is very less, deviation percentage is almost 9.52. For engineering accuracy, if the deviation is less than 10 percentage, it is acceptable. So our deviation is less than 10 percentage, so we accepted it and we continued with the numerical simulations for all other parametric studies. Next, for 10 gram in experimental, the deviation is 11.52 mm, and from LS Dyna it is 12.65 mm. Deviation is almost close to 10, but it is less than 10. And for 15 gram, in experimental, permanent deformation was 13.73, and from numerical it is 14.59, and the deviation is 6.29. As I told, for 20 grams, since all the edges are tearing, we are not able to measure both in experimental and in numerical. This is for zero point 0.1 weight percentage of CNT, how the damage is taken place and what is the deviation. So when we go for a zero point 0.1, the deformation, the deviation has got reduced compared to 5 grams. Compared to neat composites. And this is for 0.15, how the deformation is taking place. Here also the deviation is almost reduced, and it come close to 6. So this is the comparison between the experimental and the numerical values. Here I have not put the contour plots because if I put contour plots, this deformation, how it is happening at the edges, it will not be visible much clearly. So I have made it as a plane, and I have shown how the deformation is happening between the, so that we can, it can be visible how the deformation is happening. So here we can see for 10 gram, so there is a tearing in this edge and this edge. Same thing we can simulate here. So here there are small damages on these transverse edges. So for 15 gram, you can see the three edges are tearing, and here also all the edges have been completely teared in the numerical simulations. So from these comparisons, I have not included other pictures because it is going to be of a similar type. So just for understanding how the numerical is validating with the experimental, I have shown some of the sample images. So with these tests, we understood that we can simulate the same what is happening in experimental with the help of software. So we have done lot of other studies for different thicknesses of plate using the softwares. uh, since that work and all we are yet to publish, I am not adding in the presentations. So from all these studies, we concluded that when we add the CNT, the strength of the composite increases. So we have gone to particularly zero point 0.1 to 0.158 percentage of the CNT based upon our literature studies for other things not for underwater explosives. For other structural things from the literature, they told the strength of the composite increases when the CNT percentage is between zero point 0.1 to 1.15, and if you go beyond this, the strength is getting decreased. So we thought to maintain between these two ranges only. So we have taken the least and the utmost 0.1 to 0.158 percentage. And we have studied about how the deformation, tearing, and the complete damage is taking place using the software and compared with the experimental studies. So it gives us a confidence that we are able to create the same as experimental studies, and we have done for different charge weights. We have done even for 150-gram charge weights using this, and we have studied for different thicknesses of plates. We have increased the plate thickness, and other studies like behind the plate we kept water like 1 by fourth, 1 by half, then 3 by fourth, and completely filled, and we have studied all those things. So from that studies we have came to know that when it is airbagged, the damage is much higher, and when there is a water behind the plate, the damage is getting reduced. It is because whatever the shockwave which is transversing the water behind the plate gives the stiffness to the plate, and it resists the deformation and it holds it from that. So when we add the water behind the plate fully, again what it is happening is it will be incompressible. So when the first plate deforms, it pushes the second plate also. So if you provide some air gap between these two plates, what it is happening is that air gap is compressible. So whatever the first plate deformation, the second plate deformation will slightly reduce, because the air will get compressed and the fluid will take some amount of shock wave, and the second plate will not be exposed to much of the shockwaves. So this is our outcome of the studies overall. So if you have any questions, you can ask me. Thank you.
Yeah, thank you, sir. Thank you so much for this
Thank
wonderful presentation.
you. Yeah.
And I have some questions here, sir.
Yes, ma'am.
Yeah, first one.
Mm.
What novel manufacturing techniques could be employed to further enhance the toughness and the resilience of carbon nanotube toughened glass fiber reinforced composite panels?
Okay. Actually, we have fabricated using hand layup method. So in this, fiber will be there, resin will be there, and it will be applied, and we may allowed it for curing. So there are different ways of fabrication of composites. Mostly, if you see the applications in most of the aircrafts and all other fields, they will use pre-peg. It is like uh, composite with resin will be already prepared and it will be kept. No need of applying the resin on a hand or all those things. So it is like a sheet with a label. We can tear one side and we can paste it directly. So like that they will paste one over the other, one over the other. In that what will happen is uniformity will be there. When we apply the resin in hand, the uniformity getting it is very difficult. So when we go for prepay, the strength of the composite and the properties of the composite will be much higher. So composite is concerned, how we are fabricating is also a parameter in finding its stiffness. So that is one choice, and the other one we have to while curing, after they lay up all those things, we have to keep it in a compression molding. When we keep in compression molding, because of that pressure, whatever the excess resin which we have applied will come out, so that the distribution of resin inside the play between the layers will become more uniform. But again the drawback is when the pressure applied is more amount of resin will come out, and the stickiness between the layers will get reduced. So it the best method is pre-peg. When we use pre-pack composites, the stiffness and the strength will be much higher compared to all other fabrication techniques. Still, we have to go and test what is the difference between the hand layup method and the pre-pack. We have to further extend our studies, and we have to study about it, and we have to explore what is happening in that.
Yeah, okay, thank you, sir.
Thank
How might the advancements in nanotechnology influence the development of future generations of these composite materials?
Actually, when we use pure composites and resins alone, there will be a gap between the resin and the fibers. So these gaps only makes it slightly to degrade in the strength. When we use these fillers, they will go and fill these gaps and they will add the strength to the structures. But again, what type of fillers we are using based upon that the strength it is varying. It's like in chemical reaction, we use catalyst to increase the reaction rate. Based upon what type of catalyst we are using, the reaction rate depends. So same way, still it is what undergoing research. People are using different types of fillers like titanium fillers, graphene fillers, ceramic fillers, carbon nanotube fillers. So still it is going on. Still there is no concluded result that these fillers will give much strength. Everybody is comparing with their own and they are telling it is this much it has proven much increase in strength. This much it has proven much improved in strength. Still a finalized one which will give much higher strength is not yet come. It is still in research.
Okay, thank you, sir. So next question: in what ways could machine learning and artificial intelligence be utilized to optimize the design and performance of these panels underwater shock loading?
Actually, now this hand layup technique, what I have told, it is done by humans only. So whenever we do and when a machine does, machine will do whatever the instruction it is given to it. So if you tell you maintain 1 mm thickness means it will perfectly maintain 1 mm thickness. But when we do it with our hand, maintaining that 1 mm thickness is a we can nearly maintain, but exactly it is a very difficult. So when we when these fabrication techniques are given to artificial intelligence, I think the perfection will increase and that will enhance the strength and properties of the composite and which will give an uniformly distributed properties of the composites.
Okay. So, what are the environmental implications of using carbon nanotubes in composite panels, and how might future research address any potential concerns?
As for us, still whatever it is happened, they have not. There is no environmental issues because of using carbon nanotubes. So mainly these are all used for structural applications, and these structural applications when the damage is happening and all those things, there is no effect in the environment. They are not causing any effect to the environment. And even if let us say carbon is falling on the ground, it will be converted as a energy only. So it will not affect the environment. So these fillers, maybe some other fillers, if it is there, which are not there degrading, it will affect the thing. And now what is happening is instead of going for carbon nanotubes, lot of natural fibers are coming into picture. So when we start using these natural fibers, there I think it will not affect, not at all going to affect the environment. The
Okay.
use of chemicals will drastically get reduced.
Okay. So, thank you, sir. Sir, what experimental methods are commonly used to study the structural response of carbon nanotube toughened glass fiber reinforced composite panels underwater?
For underwater explosion, all the experimental studies are very costly.
Okay.
So, and facility is also not available in many places. To my knowledge, in India, only 3 places are available, and all are under government, central government, under DRDO. So we are able to do this test all these things because we got a funded project from DRDO. So with that fund, we are able to do all these tests. So for a common man, it is very difficult, and they will not allow to do all these types of tests and all these things.
Okay. So, okay, sir, this is my last question.
Yeah.
How does the structural response of these panels compare to traditional composite materials when subjected to similar shock loading scenarios?
Actually, this is very good question. When I use metals in the place of composites, metal has a very good deformation characteristics compared to composites because metal is a ductile material, composite is a brittle material. So composite cannot deform much longer, so it will start breaking, it will start damaging. but metal it will go undergo long deformation, so it will not fail much quickly compared to composites. So it will deform and it will try to withstand the structure much more. But there are few drawbacks in the metal. When we use full structure with metal, weight will increase. And the second thing, corrosion. So when weight increases, we need to provide more amount of energy to move the certain way, such vehicles. So when we need to move more, when we provide more energy to, more thrust to it, it will consume more amount of fuel. Same if I use composite with less fuel, it can travel, it can cover that distance because of reduction in weight, and the same stiffness it will composite is also going to give. And for underwater, composites are corrosive resistance. So only people are thinking to for an alternate in terms of metals, they are going for an composite.
Okay. So thanks, thanks for the useful answers. The answers are very useful. I hope the access and the participants can understand about that. So
Okay.
finally, so ladies and gentlemen, and behalf of our organization, I would like to extend our deepest, heartful gratitude to Dr. Suresh for gracing us with his invaluable insights and expertise in the session on structural response of carbon nanotube toughened glass fiber and reinforced composite panels subjected to underwater shock loading. So, Dr. Suresh's profound knowledge and dedication to his field have undoubtedly enriched our understanding of this complex subject matter. His illustration on the advancements in material science and the practical implications of his research is finding have been both enlightening and inspiring. So we are truly grateful for Dr. Suresh, his generosity in sharing his time and expertise with us today. His commitment to excellence in education and research serves as a beacon of inspiration for all of us in the academic community. So we extend our sincere appreciation due to Dr. Suresh for his insightful contributions and look forward to future collaborations and interactions that will further probable our understanding of this fascinating field. So thank you once again, Dr. Suresh, for your invaluable presence and enlightening discourse. So thank you, sir. Thank you so much.
Thank you once again. And also, one thing I want to tell to the participants, if anybody is interested to work in this field, they can contact through Teamstick, they can contact me. I'm ready to help whoever is interested to work in this field. Instead of the difficulty is we cannot do experimental test, but there are a lot of opportunities that they can work on the numerical studies and they can get explored in those areas. So already some of the tests which is available in the experiment are available in the literature. So with that we can compare and they can explore it. So if anybody is interested in this field, they can contact through you and they can reach me.
Yeah, sure,
So
sir. Sure.
thank you
Thanks,
very
sir.
much
Thank
for
you so
giving
much.
me an opportunity. Thank you
Yeah.
very much.
Yeah. Thank you,
Thanks
sir.
to Team Sticks Solutions.
Yeah.
Thank you.